Hello there, and thank you for clicking on this video. In this video lesson, we are going to explore exponential functions and their graphs. Please give this video a like if you find it helpful, subscribe to the channel for more math help, drop a quick comment to engage, and be sure to check out the practice set on this lesson to test your mastery of the concepts that we cover. So without further ado, we are going to begin with a little vocabulary. We need to make sure that we are on the same page with what we're talking about. So first off, what is an exponential function? And I just defined this past week with my own students. An exponential function is a function where the variable is in the exponent. Okay, and so just for contrast, you might have a polynomial function, say x to the third, that would be a cubic, and our variable is in the base and the exponent is a 3. An exponential, by contrast, would be this, where the variable is now in the exponent. Now, I've been using these words, so maybe I should have put this in the other order, but what is the base? What is the exponent? When we are talking about exponentials, the base is the number that we're raising to the power, and the exponent, of course, is the superscript, and that is our exponent. And we don't necessarily have to have just x as the exponent. So when I say the variable is in the exponent, there can be other things in the exponent with it. For instance, you could have something like this, okay, where you have 3 to the x plus 2, and so the x variable is still in the exponent, but there's some other things there with it. So what we're going to look at, and I'm going to do this the long way, not because I'm a huge fan of it the long way, but because I have recognized in my own classes and with my students that there is often a disconnect as we begin to rely on graphing utilities a lot. So the way this lesson is going to go is we're going to do 3 of these kind of out the long way, so that we can really look at the patterns and the connections for where these graphs come from. And then we're going to kick over to a graphing utility because it is more efficient, and hopefully we can cover all of the bases without too much time. So what we're going to do first is establish the parent function and the parent graph. Now, because exponentials have some base other than x, there's actually like an infinite number of parent functions, so to speak. So we're going to work with f of x equals 2 to the x power, but we could have 3 to the x power, 4 to the x power, and the changing of the base does change something, even though they're still within the same family. So now, to do this, what I told my students to do, they busted out their old school calculators here instead of going to a graphing calculator. And what we're going to do is take our value for x and plug that in. So we have 2 to the negative 2. Now you could throw that directly into a calculator, or you can engage your knowledge of negative exponents. So it's not a bad idea to review some negative exponents. 2 to the negative 2 is 1 over 2 squared, which is 1 over 4. And for graphing purposes, it might be nice to change that to a decimal. Okay, so what that means is we're going to go left 2 and up a quarter of the way. In other words, that point is sitting very, very, very close to the x-axis. I told my students, are you going to have to estimate that? Yes, you will, but like that's okay. Doing the next one, we have 2 to the negative first, which would be 1 over 2 to the first power, or just 1/2. And so that's 0.5. So I go left 1, and I'm going to go up halfway. Next one would be 2 to the 0, which is 1. And so when x is 0, y is 1. So we have our y-intercept. And now the rest of these are easier to navigate. 2 to the first power is just 2. 2 squared is 4. And 2 to the third is 8. And so we can round out our table with 2, 4, 8. So right 1, up 2. Right 2, up 4. and write 3 up 8. And we want to notice a couple things about that graph. First of all, we can connect the dots. So this led to a kind of a mini lesson in the middle of a couple of my classes between like what's a discrete function and what's a continuous function. So a discrete function is one where you would not connect the dots, and that would be determined by what the function was of. So I use the example, like if you're selling t-shirts for $10 each, then you can't sell half of a t-shirt. You can't sell like 3/4 of a t-shirt. You can sell one t-shirt, then 2 t-shirts, then 3, and so forth. In a continuous function, you can have values in between your integers. So it's not just I can sell one t-shirt, 2 t-shirts, 3 t-shirts, but like I could have 2.5. I could have 1.25. And what that means for us is that these points exist, but so do all of the points in between that we could have picked. And so that is why we connect the dots. Now, if we reason for a little bit here, we're never going to get a negative value for y. So even if I had x is equal to -100, okay, so we have x is equal to -100, that would be 1/2 to the 100, which would still be positive. It would be really, 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 really small, but it would still be a positive number. So when we go to sketch this in, we want to make sure that our graph does not actually cross the x-axis. There we go. Okay. And we do want to draw the arrows at either end to indicate that the graph does indeed keep going. And there we have it. So that's what the parent function looks like. And a couple of things to note about this. Notice that the graph will appear very flat for a very long time. But once it starts to curve, once it starts getting some momentum, it will become very, very steep very fast. If I were to go out one more, it would be 416. Now, also notice the relationship between the numbers and the y value in our table here. So our x's are going up by 1 every time. That's fairly normal, okay, for a table. I mean, it doesn't have to be that way, but it's not rare. Over in our y's, notice that we are always multiplying by 2. Okay, we're going up by 2, and that times 2 and having a base of 2 is not a coincidence. Okay, that is not a coincidence at all. So we're doubling every single time. And it's another way to reason why it's never going to be negative, because what you're doing is you're cutting it in half every time. And if you take a positive number and you cut it in half, you will still have a positive number. Now, that was the long way, but it is so important that as we're studying graphs, families of functions, and these patterns, that we are able to connect the function in equation form with the table of the function with the graph of the function. Right, let's move on to the next one. So the next one is like, what happens if we add a 3 on the outside? So I'm going to take my 2 to the x, same thing I just graphed, and I'm going to add a 3 to it. So I'll do a little bit of scratch work over here, but we won't belabor the point. So we'll start with 2 to the -2 plus 3. Well, 2 to the -2 is still 1/2 squared. It's still 1/4, which is still 0.5 and 0.25. And so we're going to add 3 to that. Same thing will happen when we do 2 to the -1, sorry about that, plus 3. So 1/2 plus 3, which would give me 3.5. 2 to the 0 plus 3, well, that ends up being 1 plus 3. And right about now, you should start to notice a pattern with this. Like, wait a minute. Hang on. What's happening here is we are taking all of the y values from the previous table and adding 3, which I'm pretty sure I have later on this slide, but we'll see if I remember to do it. So, okay, and we can keep going with that. So 2 to the first power is 2, plus 3 is 5. 2 squared is 4, plus 3 is 7, and 2 to the third power is 8, plus 3 is 11. Now, as I go to graph that, -2 up 3.25 puts me right there. -1 up 3.5 right there. 0, 4, so our y-intercept has slid up. 1, 5, 2, 7, and this last one actually doesn't fit on here, but I don't want to redo. Okay, and trying to connect my dots as best I can. Okay, and what we notice is that we have exactly the same graph, except it is up 3 units. Why is it up 3 units? Well, because we added 3 onto all of our y values, which then slid the graph up on the coordinate plane. Okay, and like this is what I was just pointing out. So how does this table compare to the parent function table? Well, there it is. And you can see our previous table that we filled out, and we can see that all of our current y values are 3 greater. And if you don't mess with the x's, but you do mess with the y's, what you're going to do is slide everything up or down, depending on what you're doing. So this reviews our transformations. It also gives you an idea of where the outside is for our exponential, and of course reinforces the shape of the function. All right, and this is the last one that we're going to do out the long way. Now you will notice on this one that I did change the x values. Okay, and there is a reason for that. So let's go ahead and see how this one shakes out. So we're going to start with x is equal to -5. So this one, we are adding 3 on the inside. And as we study new families of functions, one of the things we need to think about is what is the inside. In absolute values or parabolas, it's inside the parentheses. If you've been following along or you've used these videos for other units, you know that when you have like square roots, the inside means inside the square root. So with an exponential, when we say inside, what we mean is inside the exponent. So I'm going to start with -5. Well, -5 plus 3 is -2, which is 1 over 2 squared there, which is 1/4. Oh, wow, that looks familiar. We have the 0.25, except instead of getting the 0.25 at -2, I am getting it at -5. And you can probably figure out what's going to happen next. We have -4 plus 3 is -1, so that's 1 over 2 or 1/2. But instead of getting that at the -1, we're getting it at -4. When I plug in a -3, well, -3 plus 3 is 0, and 2 to the 0 is 1. And we're still noticing this, we are doubling it every time. Now, when we added the 3, we lost the sense of the doubling, and that's because we had like this vertical shift on it, which meant that like we were kind of doubling like a piece of it, but then the 3 wasn't doubling every time. So it kind of obscures that, but all right, -2, if I plug in a -2, -2 plus 3 is 1, which would give me 2 to the first power, or 2. -1 plus 3 is 2, and 2 squared is 4, and 0 plus 3 is 3, and 2 to the third power is 8. So I'm going to come over here and just erase my scratch work because we do not need that scratch work. righty. Smarter me would have paused the video there, but okay. So let's go ahead and take a look at this. So -5, and we're gonna go up 0.25. And what I want you to think about is when we did this originally, the 0.25 was at the -2. And so essentially what we've done is we've taken this and we've slid that 0.3 units to the left. So we're getting that 0.25 over here instead of over here. -4 is goes up 0.5. -3 goes up 1. -2 goes up 2. -1 goes up 4. And 0 sends me all the way up to the 8. And once again, like trying my best. When I'm doing this, I know you guys can't see it, like a weird message pops up on my screen. There we go. And yeah, so what has happened from our original graph, I'm going to go change my color over, is before we had the 0.25 here, and it has now like moved 3 to the left. 0.5, and our new one is 3 to the left. 1, 2, 4. Seriously. 4 and 8. And what's like just tricky about this, and I told my students, I said, we don't typically do horizontal translations on exponentials like first. Okay, we don't like typically do that because they are harder to see. When you're doing a parabola or something, you just trace the vertex and you can see, oh, well, that parabola went, 3 to the left. This is much, much harder to see. But if you look at the individual points, this point got slid 3 to the left. This point, 3 to the left. 3 to the left, 3 to the left, like all the way down. Every point moved 3 to the left. Now that does review those transformations because we do tend to think, oh, x plus 3, it should go 3 to the right, but it doesn't. It goes 3 to the left every time. Now, looking at the table, the way you see that horizontal shift is not in the Y column, like we saw the vertical shift showed up in the Y column. We see the horizontal shift in the X column. If I take each one of these numbers and subtract 3 from it, I will get that. And that subtracting 3 might make some like sense there. All right, so this one went left 3. Now we're going to move on to Desmos. I actually ended up not using Desmos, so just ignore that. We went to a graphing utility for the rest. So this one, if I were to look at this, my exponent here, I am subtracting 3. So that should move it to the right 3. Again, it's counterintuitive. It's like opposite of what you think. And then the -3 on the outside should move it down 3. And it did. Now, again, harder to see, like legitimately harder to see. But if I look at, yeah, because this one has like a left and a left, right, and an up, down. Let's see if I can do this. That was my original y-intercept. So we're saying this went to the right 3, 1, 2, 3, and then down 3. Aha, there it is. Okay, so that's where my y-intercept slid. A lot harder than seeing the vertex of a parabola, but that one went right 3, down 3. Okay, next one. So this has got a negative out in front. And if you've studied transformations before, you know that negatives flip things. And if you've studied radical functions, then you probably have a pretty good idea of what this flip is going to be. But let's take a look. All right, that is a flip over the x-axis. Now, I think it's worth it to explore the table here. All right. So if I plug in those same values that we were working with before, Okay. If I plug in a -2, I will have -2 to the -2, which would be -1/2 squared, or -0.25. If I, let's do the 0, okay, -2 to the 0 becomes -1. Okay, -2 to the first power becomes -2. And essentially what you're doing, that was a 0.25 there, sorry about that, is that negative took every single y value that we had in the original. Sorry, that negative right there took every single y value that we had in the original and made it negative. So we were going the same distance left or right, but now instead of counting up, we are going to be counting down. So we should be able to find those points: -2, -0.25, -1, -1/2, 0, -1. 1, -2, 2, -4, and 3, -8. And so that's literally what's happening in the table. And again, a huge, huge, huge asset, if you can connect them, is connect what's happening in that equation with what's happening in the table, with what's happening on the graph. The transformations of these functions are not just random things you have to memorize, and they don't come out of thin air. Okay, now this is another one that has negative, and as we know, negatives flip things. We already saw a flip over the x-axis, so your intuition might tell you this is going to be a flip over the y-axis. And it is. So if we can reason that out a little bit, let's try one. So if we have -2, that would be 2 to the -2. Well, -2 is just +2, and so that becomes 4. And so the 4 that was over here for the parent one now has gotten mirrored over to the other side, because that negative is basically going to flip all of your like xy's. So my 0, well, the 0 should stay the same. So because -0 is just 0, so that one stays as the 1, which gives us that pivot point. But let's take a look at 2. So x to the negative, now I'm going to plug in 2. Well, now that becomes the 1/2 squared, and that becomes the 0.25. So coming over here, and there's my 0.25. So this is a flip over the y-axis. Yay. Okay. Now this one combines some stuff. So this one was intended just to see, okay, like let's like make more of these. So we've got, what do we have going on here? We have a negative out in front. So that should be a flip over the x-axis. I have a +2, which should send it left 2, and I have a -4, which should send it down 4. And what I just did there is what's called describing the transformations. If you are asked to state or describe transformations, this is the kind of question that you are being asked about, okay? And so let's see if that is correct. All right, so this might be a little bit tricky to see, but the original graph did look like that. And so we can see, yes, it was flipped over the x. Okay, so now is like, did we slide it left 2 and down 4? So let's see what we can see here. So my y-intercept, I'm going to try to play around with that. The y-intercept for the parent was at 0, 1. So let's see if I go left 2 and down. Oh, wait, I've got to flip it first. Okay, so we're going to flip, which is going to send me down there. Okay, so we flipped it, and then we're going to go left 2 and then down 1, 2, 3, 4. And we are okay on that. So there it is. Yay. And you can probably see why when teachers start teaching transformations, this is not the family of functions that we begin with, because it is much, much, much harder to see stuff. Now, one last thing I want to explore before we close this out, and that's what does changing the base do? So we did all of those problems using a base of 2, in part because exponentials get so big so fast that the numbers will swell, and so you want to keep the base small in order to not explode your numbers too much. So the purple one is the 2 to the x, the red one is 5 to the x, and what you want to notice is basically it gets steeper faster. So you could describe it that way. Or sometimes, like, the way I see it is if you look at like that area right there, it actually seems to hang out low, because for a bit there, you can very clearly see that the 2 to the x is the bigger of the two. It starts growing earlier. But the 5 to the x, even though it starts like that big explosion a little bit later, it quickly outpaces the 2 to the x. So you might picture it this way. It's got a tighter curve to it. So instead of that, it's doing more that. Okay, it's like a sharper curve. All right, well, that is the end of that lesson. Please do not forget to like and subscribe if you found this video lesson helpful. It really helps the channel out, and it doesn't take a second to hit the thumbs up button or to subscribe. Drop a comment or ask a question below. If there's something that I covered or didn't cover that you have a question about, please let me know. And check out the practice set. I'll make sure that I'll link that below to test your mastery of this content, and I hope to see you in a future video.